Hi, everyone, and welcome to the October 4th seminar. Thanks for joining us. I'm Kara Brugman, a research scientist and the outreach coordinator for forests here at Arizona State.
And I'm Kelsey, a research scientist for the force at ASU.
We remind you, of course, that you can see videos of our previous seminars on YouTube. This video will be posted next week, and you can sign up for our listserv at force.asu.edu/newsletter to get updates when that is posted. We'll have two more seminars this semester, one in November and one in January. And I do want to remind you that the winter workshop, which will be online in January, will have registration opening soon. Currently, we have one invited speaker confirmed. We're waiting for the other ones before we make that big announcement to you all. So be sure to mark your calendars.
Okay, so we are very pleased to invite Professor Kelsey Prissel from the Purdue University as a speaker for the fourth seminar today. Kelsey and her PhD at Washington University in St. Louis and completed a postdoc at Carnegie. Then she worked as a research scientist at NASA JSC before joining Purdue. So her research focuses on experimental petrology and geochemistry. And today she will discuss the chemistry of the planetary mantles set during the early differentiation stages. So Kelsey, you can start.
Awesome. Thank you for that introduction, Kyusei. And so today I'm going to jump into discussing one of the research themes of my work, and that is thinking about what is the composition of a planet. And for Earth, we probably have the best constraints on that, but I want to think about what is the composition of its surface, what is the composition of its interior, and how has that evolved during differentiation and through time. And so the crust is probably the easiest thing to consider for what its composition is, because we live on the Earth's crust and we have samples of the Earth's crust. And so we can pick up samples and analyze them and get their geochemistry and come up with an idea of what the chemistry and composition of the crust is. As we dive deeper down into the mantle, it becomes a little bit harder, but we're lucky that we still have opportunities for samples from the upper mantle in the form of xenoliths. And so we do have a little bit of ground truth for what the composition of the upper mantle may be, and we can use that to understand Earth's interior and mantle composition. However, as we continue to dive down into the Earth, we get to the core, and that's something that we don't think we have samples of. And we can think about other planets and the meteorite record, and there are samples like iron meteorites and pallasites that might be giving us glimpses into what planetary cores look like geochemically, or what the metal-silicate equilibration might look like, or the core mantle boundary might look like in the sense of a pallasite. And thinking about what is at the center of a planet if it has differentiated. And so what we can do is consider elemental partitioning between metals and silicates, and try to back out, in the absence of samples of the core directly, we can try to forensically uncover what that might be. And so this is where experiments come in, where we can create our new synthetic samples of a planet and its core. And so in thinking about differentiation, I'm specifically thinking today about a fully molten planet where we have a metal melt that's rich in iron, and that can be analogous to the planet's core, and a silicate melt, which then would be analogous to the silicate portion of a planetary body. And we can recreate those in the lab, and we can melt these compositions at pressures and temperatures relevant to core formation and planetary differentiation, and try to track what's going on geochemically during those processes. And so I mentioned for Earth that we have almost the best idea, but still have remaining questions. But we can consider these geochemical constraints from our samples and come up with an idea for what the silicate portion of the planet is. And we can combine those geochemical observations of the silicate portion and our experiments and make inferences as to what the metal core composition may be. And of course, for Earth and now also Mars, we have geophysical constraints where that can also combine with the cosmochemistry to help us interpret what the compositions of Earth's core may be. And from those types of constraints, we have an idea that the Earth is predominantly iron core, but we also have a proportion about 10 to 15% of a light element. And so there's a lot of work that's been done to try to identify what that light element may be. But in general, we think there may be silicon in the core, some sulfur, carbon, maybe oxygen, and other light elements comprising a fraction of our core. And all of that is a reflection of the conditions of differentiation on Earth. And if we think about other planets, we interpret that other planets have cores of different compositions. And when we're comparing planetary mantle compositions or planetary core compositions, those elemental differences are a reflection of the different conditions at which those planets differentiated or formed. And I'm having Earth and Mars here as an example. And we can think about the different compositions, or we can think about the different variables that influence the elemental distribution between planetary mantles and cores. And metal-silicate experiments have shown us that variables such as pressure, temperature, oxygen fugacity, as well as composition are both very important to determining or controlling the elemental distribution in a planet. And for composition, that includes both the silicate melt composition as well as the metal melt composition. And so I'm focusing today on two of these variables. One of them is pressure, and one of them is the metal composition. And so if we're considering this Earth and Mars comparison, Earth's core is relatively rich in silicon, and Mars in comparison is relatively sulfur rich. And if we're thinking about the pressures of core formation or pressures of metal-silicate equilibration, the Earth is a larger planetary body, and it has a higher pressure of core formation than that for Mars. And so today, one of the main questions that we are asking is, how does pressure affect metal-silicate partitioning? Because we want to know for planetary cores how the elements would distribute between the core and the mantle. And I'm specifically focusing on silicon-bearing cores like that for Earth. And so there are two different variables here. And so throughout the talk, we're going to try to disentangle those two. And why is this important? Well, a lot of our understanding of chemical behavior between metals and silicates comes from experiments that were conducted at relatively low pressure. And what we have to do when modeling core formation is take those chemical behaviors that were determined at low pressure and extrapolate them to higher pressure. And so we want to know, sorry, my internet broke down. But so we want to know if we take these 1 GPa data, can we apply that to higher pressures, or does the behavior change when you go to higher pressures? And this is not a new idea. There have been decades of studies on metal-silicate partitioning and thinking about this very thing. Can or do metal-silicate partitioning behaviors change as you go to higher pressures? And more recently, for iron and silicon liquids, there was a study that identified an effect of pressure on the partitioning of select siderophile elements listed here, that these elements, their behavior changed in the 1 to 11 GPa range. So if we're thinking about extrapolating to 40 and 60, and we're already able to observe chemical behavior changing in that 1 to 11 GPa range. And so for this study, we are focusing on iron silicon bearing cores and looking at the partitioning of some elements that may have a pressure effect in this 1 to 10 GPa range. And our study is looking at 10 GPa behavior and comparing that to previously published data at 1 GPa. And so looking into the methods for this project, when we are doing a metal silicate equilibration experiment, our starting material is a mixture of metal and silicate. And so for this project, we have a natural basalt composition that is our silicate, and our starting material is approximately 70 weight% silicate and 30 weight% metal. And we're loading that starting material into a single crystal MgO capsule. And the single crystal MgO capsule has benefits over a polycrystalline capsule because the melts don't migrate along the grain boundaries. And we are doing all of this in a multi-anvil, and so we're specifically using the 10-5 assembly, and I have the assembly parts, including that single crystal capsule pictured here. And so all of these experiments were conducted in the 880-ton multi-anvil at Johnson Space Center, and we conducted every experiment at 10 GPa, and we want the metal and the silicate to be molten, so we're at fairly high temperatures. Once we recover the sample, we cut and mount and polish it, and we analyze the major element composition with the electron microprobe. And so these analyses were also done at Johnson Space Center. And for the electron microprobe, we have this backscatter electron image that we took of one of our experiments. And what I want to show here is the metal balls down at the bottom, these circular metal blebs that are bright white, and the light gray matrix throughout the sample, that's our silicate melt. And when we are quenching the sample, there are quench textures of like a silicate mat that form for the silicate melt. And so what we're doing when we analyze the compositions is trying to do a broad beam to try and average out what that composition might be for that microcrystalline quenchy texture. But for some of the trace elements that we're studying, the elemental abundances in our metal or in our silicate, depending on the element, are below the detection limit of the probe. And so for that, we have to do some laser ablation ICP-MS in order to get those trace element compositions. And I have here a video of one of our laser ablation spots. And so we're centered here on a metal bleb. You can see the bright white in the reflected light. And if we start the video, we'll fire up the laser and get a nice pit and ablate that bleb. It's about 40 micron diameter pictured here, and those green spots are showing you where the corresponding silicate points were going to be taken after this metal. And so once we have our elemental compositions of both the metal portion of our experiment and the silicate portion of our experiment, we're able to use those to calculate the partitioning between the metal and the silicate. And so we'll go over that in a bit. And okay, for the starting materials, so I mentioned we're interested in looking at pressure, but we're also interested in knowing what the effect of silicon metal is on the partitioning of these trace elements that we're studying. And so we have a starting material that is a mixture of silicate and metal, as I described, and we pick the trace elements that we're interested in studying, and we dope that metal component with the trace elements that we're interested in. And so this is a picture here. I'm mixing it by hand in a mortar and pestle with ethanol to aid that. And we have a nice mixture that we start as our base composition. But then to form our experimental series for this project, we are conducting all of the experiments at the same pressure and temperature, and the variable that we're changing across our experimental series is the amount of silicon metal in the experiment. And so we take that composition I just showed you and we add silicon metal to it. And so we create a series from 0% silicon up to 10 weight% silicon metal, and we have it spaced out in 2 weight% intervals for the starting material. And so this is going to be how we design the experiment series to investigate the effect of that silicon metal content. And I wanted to show some of the chemical results from that just for the major elements. Here on the y-axis is the weight% of iron analyzed on the electron microprobe, and on the x is the weight% of silicon analyzed in the metal of our experiments, so the bright white. And what we find is that we have these nice clusters for our experiments that form a great series of experiments with different metal silicon contents. And so that's pictured here. And this is how we are looking at the elemental partitioning and how it changes with the silicon metal. And so once we have our experimental series and our chemical data, what we want to do in order to bring this into a variable that we are able to apply when we're doing models of core formation. And ultimately, what we're studying here and how we're doing that is this epsilon interaction parameter. And so just to give a brief introduction to what this interaction parameter is, it essentially it's used to calculate the activity of a specific element in the metal. And this interaction is specifically for the silicon in the metal. And so looking at this interaction parameter will tell us how an element will respond to increases in the silicon content of a metal. And so if the interaction parameter is positive, that indicates that the element will become less siderophile as you increase silicon content in the metal. And so that means this element will want to stay in the silicate melt or the mantle rather than go into a silicon-rich core. And on the flip side of that, if the interaction parameter is negative, that's telling us that the element wants to follow silicon into the core. And so we're interested in coming up with what this epsilon is for each of our trace elements. And so how we calculate that is we take the compositions that we analyzed for the metal melt and for the silicate melt, and we come up with the traditional partitioning coefficient for each element. And then we take that partitioning coefficient and we ratio it to the partitioning coefficient of iron. And this is what's known as the metal-silicate exchange coefficient. And so once we have the metal exchange coefficient or the KD for each element, we can take that and use it from each experiment. And so I have this schematic here to introduce the next plot, which the y-axis is going to be that KD value that we calculate for each experiment and each element. And the x-axis relates to the silicon content of the metal melt. And so towards the left, you're increasing in silicon in the metal. And if you have a high KD, that indicates that an element is more siderophile. It's going to want to partition into the metal. And if you have a lower KD, that means it's less siderophile. It's going to prefer to stay in the silicate melt. And so we have our silicon series of experiments, and we can calculate a KD from each one and plot it as a function of the silicon content in the metal. And once we have that data, we can fit a line to it. And in this space, this line, the slope of this line is how we're going to quantify this epsilon parameter. And so in this example that I'm showing, the slope of this line is positive. So this is a positive epsilon parameter. And so if we look at the trend here, as we increase the amount of silicon in the metal, the element is becoming less siderophile. And so that's that positive parameter. And it's important to note that because our experiments are all conducted at the same pressures and temperatures, that this is the epsilon for that element at this specific PT condition. And so now just to show you what this looks like in practice, the Y and the X are parameterized a little bit differently than what I was just showing, but the way that it's parameterized is what enables us to calculate directly from the slope. So the slope of this line that you fit through your data equals the epsilon parameter. And we're able to look at the uncertainty on that slope and intercept and provide a relative uncertainty for the epsilons that we're calculating for our experiments. And so back to our major motivating questions here is, how does pressure affect metal-silicate partitioning? So we are asked, how does the silicon and metal affect that as well? And we can quantify that with these epsilon parameters for each element that we're interested in. And then to move forward and think about how then does pressure come into the equation, we can look at this epsilon and see if it is the same at 1 GPa as it is at 10 GPa. And so that's what we have done with our 10 GPa data, is compare it to previously published epsilons for the same elements at what that were derived from experiments conducted at 1 GPa. And so here's a plot of the epsilons for a suite of elements listed at the x-axis. And this is from a previous paper, Ryder et al. 2020, that did a similar study looking at 10 GPa data and 1 GPa data. And their finding was that the epsilons for these elements studied didn't change significantly between the 1 and the 10 GPa. But now if we add our data as well as some data from a more recent study, we're starting to identify some elements for which there is a pressure effect on this epsilon. And so in our study, we identified this for bismuth and antimony. And then in a Ryder et al. 2023, they found a pressure effect for niobium. And so now you see that the 1 GPa data is significantly different than the 10 GPa data. And while the epsilons are all positive and they're above that dashed line at 0, it looks like the 10 GPa data, the epsilons are at lower values than at the 1 GPa. And so we found this for antimony and bismuth, and to look at other studies that have also looked at this epsilon for antimony, we find that our results are pretty consistent with previous studies conducted at lower pressures. And so what we're finding is that as you go to higher pressures, the epsilon is decreasing. And so what that is telling us is that as you go to higher pressures, in this example, antimony is becoming more siderophile, or you're going to be able to put more siderophile or more antimony into an iron and silicon bearing core at higher pressures than at lower pressures. And so this is consistent with other studies. And what's interesting when you look at this plot is if you look at the 1 GPa data, the interaction parameter is quite high, somewhere between 40 and 70 or so. But there's either a sharp drop at the 1 to 4 GPa range, because you see that it decreases for those 2 GPa data points, or there could be a more gradual change as you go towards the 10 and 12 GPa points that we see. And so whether or not this is a gradual change or an abrupt change, I think requires additional study kind of in between these pressure ranges, but it's consistent that we're seeing at higher pressure, this interaction parameter is decreasing. And so that was antimony, but we've also been thinking about bismuth because we found this pressure effect. And I want to bring up this Ryder et al. 2019 model for core formation on Earth that was trying to match to model the mantle abundances for these 7 different elements listed here. And their models for core formation in this example were based off of data that was generated from 1 GPa piston cylinder experiments. And what they were able to do with this model is match the observed mantle abundances with a core formation model for 5 of the 7 elements that were being studied. But as I've highlighted here, 2 of these elements, the model was not reproducing the estimated abundance in Earth's mantle for bismuth. And so what we are excited to then now take our interaction parameters and apply it to is this problem where we've found that with our data, our results are indicating that bismuth would start to partition more into a silicon-bearing core at higher pressure. And so it's going to be more siderophile at higher pressures. And so if we were to model core formation and incorporate that change, we would be able to put more bismuth into the core, and that would result in a lower calculated concentration of bismuth in the mantle. And if you look at this previous mismatch for bismuth, if we were able to incorporate that effective pressure, we might be able to then reconcile the gap between the observation and the model. And so this is an exciting implication of the findings that we presented today, and I'm going to be presenting on this in more depth, specifically just the bismuth problem, or solution rather, at AGU in December. And so in summary, we've studied a range of elements, and of the elements that we studied, we found a pressure effect only for 2 of them. And that pressure effect was for bismuth and antimony. And so that tells us when we're modeling bismuth and antimony at higher pressures, we need to incorporate this change in behavior at higher pressures. As I mentioned, exactly where this change is happening in the 1 to 10 GPa range may be debatable, and the reason for that change is still up for discussion. So previous studies have hypothesized that there are structural changes both in the silicate melt as well as in the iron melt. And there's even potential structural changes for iron and silicon bearing melts specifically, which might be why we're seeing this effect in our iron and silicon melt series. And so I want to end just to kind of think about this problem moving forward, trying to identify why elements behave differently at higher pressures. And so we studied these 8 elements highlighted here, but we only found a pressure effect for 2 of those 8 elements. I also here have my collaborators on this project, Kevin Ryder, Jake Satera, Justin Simon, and Jocelyn Richardson. And so we are getting a little bit more data. We have one last round of laser ablation data to get on our experiments, but then we're excited to put this result out into the journals. And we're still now scratching our heads as to why antimony and bismuth were the only 2 elements that had this pressure effect. But what's exciting is to start to continue across the periodic table and see if we find additional patterns that arise. And so another one of our collaborations is with our colleagues at Tulane University, where we're studying nitrogen and phosphorus. And similarly, we are finding effects of pressure for these elements. And so now we're seeing that there's potentially a correlation with this specific group of elements on the periodic table, the pnictogen elements. And so seeing this pattern helps then identify why there might be a change with pressure, and it might have something to do with these elements and their bonding structures specifically. And so I want to call out Akanshu. He's the graduate student leading the work for the nitrogen and phosphorus, and he's going to be presenting our results from both multi-anvil experiments as well as diamond anvil cell experiments at AGU this fall. And then moving on, again, still considering this effect of pressure on the metal-silicate partitioning, we have colleagues at Harvard who are also doing a similar approach in collaboration with our group, where we have conducted multi-anvil experiments, and they are conducting diamond anvil cell experiments and looking at these changes in element behavior with pressure. And so Chiara is going to be presenting that at AGU as well. So I didn't present that here today, so that way you will come to their talks and posters. And so this is a general theme of my research over the last couple of years, thinking about metal-silicate partitioning and how it changes at higher pressures. And this study, we were looking at 10 GPa, but Kelsey, you tell me this is important for Earth, right? And so that's extrapolating even further to higher pressures than what we've studied here today. But it's interesting to know that even though we're just comparing from the 1 to 10 GPa, we're already finding changes in the elemental behavior. And so it's worth studying further at higher pressures to see, does that continue? Do we see more changes as we go to higher pressures, or is the change only in that 1 to 10 GPa range? And so that's the collaborations with Tulane and Harvard with the diamond anvil cell experiments. That's something that we're able to start to address for those elements that we're studying. But one of the hard things about this is as you go to higher pressures, your sample is getting smaller. And everyone in this audience probably is familiar with that, as it's a function of the techniques that we're using for obtaining high pressure in these experiments. And I have here a backscatter electron images of a piston cylinder experiment to the left, a multi-anvil experiment in the middle, and a diamond anvil cell experiment to the right. And so these are backscattered electron images. So again, the bright white is our metal and the light gray is our silicate melt. And as we go to higher pressures, the samples get smaller and smaller. And for the diamond anvil cell experiment, we're able still to get a couple of electron microprobe points on our phases of interest to be able to calculate those partitionings. However, if we wanted to study trace elements that require something like laser ablation ICP-MS or some other analytical method, we're now kind of limited by our sample size because we're not going to be able to necessarily put a laser pit and get a clean sampling of our metal in that small experiment. And so this is when I get really excited about force. So I wanted to give a shout out to the two presses that are going to be or already have arrived at your facility. And I think that they're really exciting because it opens this window to look at pressures that are directly relevant to planetary differentiation. Instead of having to extrapolate our pressures, we can just conduct it exactly at the pressures that we believe cores are equilibrating at for Earth and Venus and Mars. And so these are things I'm excited, and also that with the advantage of having the larger sample volume, there's a potential to then be able to do more of these geochemical analyses on those high pressure samples. And another thing I'm really excited about is the lab that we are building at Purdue. And so I just started my position this semester, and so I just arrived here, and we are going to be bringing a suite of experimental equipment and analytical equipment to campus. And so I just wanted to advertise to this group specifically that there is going to be an experimental petrology lab at Purdue. And excitingly, we already have our multi-anvil press on campus. And so that's something I'm working on this semester, is getting that up and running. And so be on the lookout. We're hiring grad students and we're excited to collaborate with everybody. So I'll end here just to put my conclusions back up, and I want to thank everyone for your attention. Thank you.
Thanks, Kelsey, for a great talk. We do have one question in the Q&A. How does the electronic structure of these elements contribute to your results?
Yes. So this is something that I was kind of alluding to. The answer is I don't know yet. But this was something that I was alluding to in like seeing this pattern of the pnictogen elements having this pressure effect. I've started to think about it, and because we're looking at silicon-bearing metals, there are things like arsenosulfides or arsenosilicides and pnictogen silicide bonding that I'm wondering if that's, this is just, I haven't concluded this, but it's things I'm starting to think about as we see these patterns arise, that it could be some sort of bonding between the silicon and this group of elements that's resulting in the different effects at different pressure.
Okay, and we have another question in the chat from Rick Hervig. Did I see correctly that there is also a pressure effect on niobium partitioning?
Yes, so that was something that the paper just came out in 2023. It's Ryder et al., and they had seen an effect for niobium as well.
Another question, what do you think about the REE partitioning? I'm curious about if they have a pressure effect.
And that's a great question. And we weren't looking at that here. One of the things, so for the rare earth elements being predominantly the 3+, I don't know if it could be that the change in the silicon content here, that's also kind of corresponding with the change in the FO2 is leading to differences in these elements, specifically with their p orbitals and that kind of multiple valence states that they exist in. And so I would, if that's what's going on, I'd expect it not to really affect the rare earth elements as much, unless you were able to get to extreme conditions where they were changing. But that's something that we've been considering for arsenic, for example, or like thinking about 3+ versus not 3+ elements. I'm going to go to here. So I mentioned that one of our collaborators is Jocelyn Richardson on this project, and she works at the beamline at Stanford, at the Stanford Linear Accelerator. And one of the questions that we were trying to think about is what is the oxidation state of these elements in these metals and as well as the silicates. And for arsenic, and it came as a function of just doing the calculation, because when you calculate those KDs and the epsilons, you have to assume an oxidation state for the element. And so when I went to do this, I realized like, oh, we have to assume an oxidation state. And there's kind of a question as to whether there's a 2+, 3+, or 5+ oxidation state for arsenic in these systems. And this is in other papers that have hypothesized those different oxidation states. And so what we did at SLAC was to directly analyze with arsenic zanes the oxidation state of our arsenic in our samples. And what we found was that it was all arsenic 3+, which there's a nice study that looks at arsenic and silicate melts by Masiag and Bernan that found the transition between arsenic 3+ to arsenic 5+, and it's at way higher oxygen fugacities than what we're at. So if anything, it'd be starting to get to lower oxidation states for arsenic that are lower than 3+. But we found all 3+ in our samples. And I bring this up when you're asking about rare earth elements, just because the things that I think are underlying the effect we're studying here have to do with that p orbital space of the periodic table. And so the things that I've been thinking about, I don't know if it would translate to the rare earth elements.
Okay, we have another question, although he's noted that he thinks you kind of answered part of that in your last answer. But Daniel Hummer asks, he says, thanks for a great talk. I noticed in your plot for results with different elements that each element had an explicit charge listed. When you doped your experiments with trace elements, did you dope with metallic element or a compound where the element was in that particular oxidation state? And did you find the oxidation state made a big difference?
Yeah, so I did start to answer a little bit, but when we added them, a lot of them we added as metal. Some of them we did add as oxide, but that addition was the same across all of our experiments. So that shouldn't, the effect that's happening with FO2 is because of the different silicon that we're adding. But one of the things, so in terms of what is the oxidation state of these metals, yes, we're assuming them based off of other observations, previous studies. You can look at the partitioning as a function of FO2, and there's the slope of that relationship can help you back out the oxidation state. However, in silicon-bearing systems, we find like these silicon-bearing metals, you find that method of estimating the oxidation state kind of breaks down a little bit, which is why there start to be a little bit more questions. And so it was really nice to look directly with the Zane's method to kind of answer this question. And arsenic in particular was one that I found like in 3 different papers, all saying 3 different oxidation states for their calculation. Whereas for the other elements, they usually, there's one that everyone agrees on. But then the other thing about oxidation state to note is that with this KD approach that we're doing when we calculate when we take our metal silicate partitioning coefficients and ratio it to the D for iron, that's kind of a way, not necessarily to like eliminate oxygen fugacity effects, but to try to normalize for them. So at the different oxygen fugacities, like your D for iron is how we're calculating like the oxygen fugacity relative to iron wustite. And when you normalize to that D for iron, it kind of it tries to normalize out that change in the oxygen fugacity and the behavior of iron in this system.
He says that makes sense. Oxidation state just is whatever it is at that particular FO2. Thanks. If you would like to ask a question verbally, you can also raise your hand and I'll unmute you. Okay, Kisei, go ahead.
Hi, this is a nice talk. And you said something like bismuth and antimony becomes more siderophile with increasing pressure, right?
Mm-hmm.
And how about did you differentiate the effect of pressure and the temperature and the effect of I'm not sure, maybe you performed the experiment. For the silicate, probably you stick to the maybe one composition, maybe probably the periodic one. But yeah, I'm curious about like how you differentiate the pressure effect and the temperature effect.
Yeah. So one of the things that we tried to do with this in our experiment, all of our experiments were conducted at the same temperature. And when we compare to the 1 GPa data, they are sometimes at slightly colder temperatures because you don't have to go as hot to melt at the lower pressures. And so there's the way that when you're comparing them, as I did on that plot, you have to correct for that. And so there is a way to kind of correct for what the temperature is. The other thing, and thinking about temperature that I'm going to talk about a little bit is the temperature gradient in the sample. And so one of the things that I did for this project is we were originally starting out with pretty large capsules because we're using these pre-machined single crystal MgO capsules. And they were slightly taller than the usual 10-5 assembly. And so I used the spinel growth method of looking at the temperature across the assembly, and was able to map out the temperature for our crystal or for our capsule and see that half of our capsule was significantly colder than the other half. And so when I was originally processing this data from those experiments, I included pretty large error bars on the temperature as well, and let it, calculated it as, 1800 or the 2000, calculated it as 2200, calculated as 1800. I was looking at that effect, and surprisingly, or maybe not surprisingly, the results were always the same, that you have this resolvable difference in pressure. And so if I were to go back to, let's see here, sorry. If I go back to this. And so these error bars are pretty large on here, and that's because I was kind of giving it all the uncertainty that I had from the analyses, from the temperature, from any sort of uncertainty. And so that's why you see these ones are larger than the other study that was presented on this plot. And even like despite propagating all of that uncertainty, there you can still resolve this pressure effect for these two elements. And so moving forward, I mentioned that we have another round of experiments that we're analyzing, and to go back to this one. And so then what I did was I redid all the experiments in a smaller capsule. So we have these shorter capsules that have a smaller temperature gradient. And my hope is that the error bars, when I'm considering all of this uncertainty, will be smaller. So we're waiting for that new data, and then I will calculate it and hopefully refine that plot that we were just looking at. And it could be that there will be other elements that then have a resolvable effect of pressure. But we're pretty confident that in the bismuth and antimony ones, because even despite all that uncertainty, they're still resolvably different.
Do we have any other questions? Let us thank our speaker, Kelsey, for giving a great talk today. And before you log off, I realized I forgot to say something important that has happened this week. Sorry, Kelsey, that I forgot to include this in the opening slides. But we just yesterday did our training for Jasmine. So Jasmine has been installed. We did our training on the Dia, and she is a beautiful machine. We're really excited to start working with her. And I think Kelsey was talking about making some assemblies basically as soon as possible. So yeah, so thank you all for joining us. Thanks again to Kelsey.
Thank you for having me.